So yeah, thank you for that, Marcus. So my name is Peter Brown. Some of you I know really well, former colleagues, clients, etc. And some of you won't have heard of me at all. I work at a company called 42 Technology. We're part of the consultancy scene in Cambridge. We're a technology development consultancy. Those of you who know the history of the area know that the inkjet business here grew up out of the consultancies, Cambridge Consultants, and then latterly TTP, of course. I started at TTP, but you'll find that none of them are here anymore. We are probably the only kind of the main well-known consultancies who are still in the industry. So, a bit of context, of course. We heard this morning from Carl at Xaar, and then of course from Cabot and so on, that Aqueous inks it's almost like the time has come. They're really breaking through. People have done them for years, of course. Inkjet started with HP in water-based inks. But in the industrial sector, it's kind of lagged behind. And it's because, of course, it just takes ages to dry. It takes a ton of energy to evaporate the water molecules, and then you've still got to get them out of there as well, otherwise the thing just stops. So, what are we going to do to address that? So solvent inks, they dry really, really fast. And that means you can print on just about any substrate you like. And that's a great thing. Everything from coding and marking all the way through to page-wide presses and so on. The challenge is, of course, is that they're not very nice molecules. Biologically speaking, they tend to be a bit nasty. And in fact, there have been rumours around for quite a long time that MEK might even be reprotoxic, and if the EU confirms that, that's big problems, because then it's a CRM molecule and the regulations go through the roof for that. So if you're trying to ship that across country lines and so on, that becomes an issue. And of course, where the EU goes, usually the other regulators follow pretty soon after that, the US and so on. Ethanol, another common molecule that we use as a solvent carrier. Everyone knows that that's regulated heavily, but it's getting tighter and tighter. It's getting worse and worse. There are plenty people who work with solvent-based inks are telling me that this is becoming a bigger problem, particularly in South America and places like that where it used to be relatively lax. And then, of course, there's the cost issue. Water is, well, it's dirt cheap. Compared with MEK or ethanol or whatever, it's 100 times cheaper. So the drivers to go to aqueous inks are huge. And of course, with Xaar's Aquinox technology, it's now there waiting for you, and others as well, of course. But Xaar has been good enough to bless us with their presence here today, so they get top billing, of course. The physics of this is well known. Water is an odd molecule. We learn that at school. You've got the hydrogen bonding between the molecules, and that means that they bind together tighter than just anything else you might expect of that size. So it takes more energy to evaporate. The boiling point is higher. The vapor pressure is a lot lower. You just need to break those bonds to get it to evaporate. And the challenge is that this is fundamental physics. There's not a lot you can do to change that. You've got to engineer your way around that. You can't change the physics. So what are we going to do? Well, of course, the most common approach is hot air drying. This is something HP's been doing ever since they started it. It's easy. Everyone knows how to do hot air drying. But the problem is it's very inefficient. You spend an awful lot of time heating up an awful lot of air, and the vast majority of that air doesn't go anywhere near what you're trying to heat up. In addition to that, it also heats up everything else it touches, like the substrate and so on. So if you're trying to print onto polymer film and so on, that could be bad news. They're very sensitive to those things. It's bulky and it's noisy. Anyone that's ever been anywhere near one of the gigantic page-wide presses and so on will tell you that you need air defenders. These things are loud. Now, we're a consultancy, and it wasn't so very long ago that a client came to us with exactly this problem. They said, what can we do that's different from hot air drying? So you sit down, you go through all the logical ways in which you might be able to heat up some water. And we're not talking a lot of water in the grand scheme of things. So you look at broadband IR. People are doing that already, often in combination with hot air drying. Again, it's not very efficient. Even if you combine it with hot air and you've got the broadband IR, you're struggling to get that above 10% efficient. That's an awful lot of energy, expensive energy, that you're almost literally chucking out through the roof. So you think, well, how can I make that more efficient? Narrowband IR. Part of the big issue with water is that it's almost completely transparent, particularly in the visible area. But if you go to around 2 to 3 microns, it's almost black. It absorbs just about everything. Problem, the LEDs that you want to use are really, really expensive. You know, you're talking 10 to 20 pounds for one LED. Not attractive if you're going to need tens of thousands of these for the biggest possible applications. Some applications, you might have a metal substrate. We've not talked a lot about that here, but it's a fairly common application these days. Maybe induction heating will work. Well, only indirect heating of the ink. You're actually heating the substrate. Only eventually does the ink get heated. And by the way, there's some subtle effects in there you need to think about. You can't just use any old metal. There's a reason why the pots you use in your induction hobs are made of very specific type of metal. You can't just chuck copper or whatever in there and expect it to work. And then, of course, the other common heating method that everyone knows about for water is microwaves. Now, the microwaves that you use in your oven at home, or even in the ovens that you have in industrial scales, it's actually an irradiation. It's an electromagnetic wave. So it's the same as shining a light on it or shining IR on it. Now, microwave are very difficult to produce. There's no such thing as a microwave LED. There's no such thing as a lamp for microwaves. So they're quite expensive bits of equipment. They're difficult to control. It's not very easy to make a lens for microwaves. So that has problems too. Now, speaking as a physicist, I know there's some of you here, Guy, Dan, we're often told to keep the science to a minimum. So all I'll say is this, for the next 2 or 3 slides, if you're a bit squeamish, just look the other way, all right? Now, dielectric heating is not a new process. It's been known about for a long time. It's all to do with how the molecules in the material that are experiencing the time-varying electric field react. Now, when it comes to something like water, you've got the vibrational modes of the molecule, you've got the rotational modes of the molecule, and they all have fixed dipole moments. And actually, the microwave ovens that we were talking about a moment ago, they work on the rotational modes of the molecule, which just so happens to be about 2.4 gigahertz. By the way, that's the same frequency your Wi-Fi modem works on. Which is, and it's another reason why your mobile phones and your satellite TV doesn't work so well when it rains, because the water absorbs it. But what happens is that if you add some salt into the water, you add some ions, and the ions will also move as a result of the electric field. And as those ions move backwards and forwards, they generate friction, they bump into other water molecules, and it generates heat. Now, all these things happen at different frequencies, and it is this parameter here, what physicists call the imaginary part of the relative permittivity, is the important thing. Now, if I was to shine a light on this looks a bit like the absorption spectrum of water. But if I was to put an electric field in the way, this is related to the conductivity of the water, which is quite interesting. So, if I was to put an electric field across some water, some salt in it, time-varying electric field, it starts absorbing, starts generating heat, that's dissipating power, and the power that you dissipate is actually quite simple. It depends on the frequency, it depends on the material properties of the water, and it depends on the square of the electric field, and that's it. And this, by the way, is what is real data for water, not that cartoon. And you can see that as you go to frequencies of tens of megahertz, which is quite an important one because all this is regulated. You can't just start chucking radio frequency electromagnetic waves around and not expect someone to notice. A client of mine actually had a mobile phone company pop round recently and say, "Oh, there's a bit of interference around here and it's your oven. Can you fix it, please?" So, having said all that, why is this exciting? Well, there's some very, very good reasons why this could be a very good application for industrial inkjet printing that we haven't really looked at yet, and I think we need to. One of the main things that jump out is how efficient this is. RF heating has got this almost, I'm a physicist and I still think it's magic. It only ever sucks energy out of the external circuit if there's something in the way that's capable of being heated. So that means your water with a little bit of salt in it, and there's often salt in inks. It doesn't heat the substrate. It doesn't heat the air around it. It just heats the ink. And what's more, it just heats the ink uniformly all the way through. So most heating processes, you're heating the outside of the ink first and using conduction to get into the middle. So you're heating everything uniformly. I think that's absolutely brilliant. But that 75% efficiency is massive compared with the 10% of hot air combined with broadband IR. It's a highly scalable process. Now, as I said, this is not a new technology. You can have industrial ovens out there right now. You can buy them at tens of kilowatts. That's a lot of energy. But if it's 75% efficient, you're using that a lot. Compare that to the quarter of a megawatts that you might find on a gigantic corrugated page-wide press, for example. What I like about this as someone who's applied physics and working with engineers to make new technologies is you've got considerable freedom to design this thing. The way you change the shape of the electrodes, you change the shape of the electric field, and you can start to develop, consider applications for direct-to-object, printing onto 3D patterns and so on. Initially, you might think, well, sheet-fed and so on, that's the best application for it. But there's absolutely freedom to look at other more interesting things. And last, and definitely by no means least, if you talk about hot air drying, there's no IP there anymore. It's all been done. You're going to have to work very, very hard to try and squeeze something new into there. But this is a relatively virgin territory, particularly for the inkjet industry. I think there's tons of IP there, and you wouldn't be surprised to learn that there's an awful lot of stuff in here I haven't put in there, because it's up here. But there's definitely scope for tuning this, for example, in ink formulation and so on, to get something that's genuinely novel and interesting. Time's nearly up. I've talked quite fast. There's a lot to fit in, but I think the message I'm trying to get across here is that we're all seeing a big movement towards water-based inks. It's happening, and it's been driven by an awful lot of factors. We all like to think it's because it's green and so on, but also, frankly, just solvents are nasty. Long gone are the days when you can have wash bottles of MEK lying around and just use it to slosh things off. I'm pretty sure that's going to have to go soon. So having accepted that, and the barrier for aqueous inks is almost completely gone now. You can just go and buy the print heads, it's there. What are you going to do to address the elephant in the room? You might even have half the amount of water you used to have if you're using ZAR's technology, for example. But you've still got to evaporate it. How are you going to do it? And how are you going to do it in a way that's commercially interesting? And I think this is definitely something worth looking at seriously. Thank you.